Hello, I welcome you all. The problem reads that the girl has a mass of 40 kg and the center of mass at G. If she is swinging to a maximum height defined by theta equal to 60 degrees, determine the force developed along each of the four supporting posts, such as AB at the instant theta equal to 0 degrees. The swing is centrally located between the posts. This problem is coming from the Engineering Mechanics and Dynamics, 14th edition by R.C. Hibbeler. In this particular section, we are going to be using the conservation of energy principle. If you remember, in the previous section, we were using the principle of work and energy. So let's just define what this is. What is this conservation of energy? So conservation of energy, it states that during the motion, the sum of the particles' kinetic and potential energy remains constant. And for this to occur, the kinetic energy must be transformed into potential energy and vice versa. And we can express this conservation of energy using this particular equation. All right. So we have T1 plus V1 equal to T2 plus V2. T1 is the kinetic energy and V, so T is the kinetic energy and V, so T is the kinetic energy and V is the potential energy. So we have both gravitational potential energy and elastic potential energy, right? So we can refer to this particular equation as conservation of mechanical energy or simply just the conservation of energy, right? So the conservation of energy equation can be used to solve problems involving velocity, displacement, and conservative force systems. Okay, so a conservative force itself is a force that is independent of the path, right? It just depends on the position, right? The initial position and the final position, right? So it is generally easier to apply than the principle of work and energy because the equation requires specifying the particle's kinetic and potential energies at 2 points along the path rather than determining the work when the particle moves through a displacement. So basically this is what we intend to use. So let's begin working on this particular problem. Right. Okay. So what are those points? So here, let's say we have this one point. This is the first point here, point 1. Okay. And let's also pick another point. Let's pick another point. Let's say through here. Let's also pick another point. We say maybe point 2, somewhere there. All right. So let me say we have point 2 somewhere there. Right. Okay, so let's draw the free body diagram. We'll have the weight. We'll have the weight acting through the center of gravity. And then we are going to have components of this particular weight. One component along that direction like so. And another component in that direction like so. Right? And then we have a coordinate. We're going to have these coordinates. This one we are calling it the n coordinate, and this one we are calling it the t coordinate or the tangential coordinate. Right, so let's say this one is the n and this one is the t, tangential coordinate. right? And this is our W, okay? And we do have this angle here. So this angle here is the same also here, right? This is the same angle here, right? You agree? This is our theta. Okay. So if that is the case, then you expect this one here to be W cos theta, all right? And this one is W sine theta. Okay. So let's write our equation, the conservation of energy equation. So we have T1, which is the kinetic energy at point 1, plus V1, which is the potential energy, and this is gravitational and elastic potential energy. This is going to be equal to T2 plus V2. Alright, so let's read through again. We see exactly what is happening. So we've been told that this girl has weighs 40 kg and has a mass at g, and if she is swinging to a maximum height defined by theta equal to 60 degrees, determine the force developed along each of the 4 supporting posts. So we have 4 posts. You can think of these like this. Okay, we have 4 posts like so. There are 4 of them. Okay, so this is basically what is happening. 4 of them, and this is a swing. So and then you have a swing there, right? Moving up and down, right? Up and down and so on. So this is the kind of a post. So you can say this is B, this is A, you can call this C, maybe D, E, F. Okay, so you have these posts. This is, we want to find the forces in this particular post. And when you look at these particular posts, they are truss structures, okay, or 2 force members, right, connected using a pin at A. So before we even go that side, let's explain what is happening here. So at A, at point number 1, we can simply say the swing is temporarily at rest. So it's like it is held there, okay, at A at 1.1, and later on it is released, right? So we can simply say the kinetic energy at point 1 is equal to 0, because we are assuming it is at rest, right? Okay, so we only have the potential energy here, the gravitational potential energy, right? So what do we have? So let me choose the datum point. Let me choose the datum point. So let this be my datum point. All right, sorry. Okay, let me lift it up. I place it where it's supposed to be. There. Okay, so let me just write this once more again. So it said this is our n. Okay, so this is my datum. This is quite very important, especially when you are defining your potential gravitational potential energy. So this is my datum. So therefore I'll say what let's define our potential gravitational potential energy, okay, for point 1. So it's minus, this is minus W H1, okay, and then equal to, we are going to have the kinetic energy, and is positive mv2 squared, and then of course we have W H2, where H1 is just equal to R cos theta 1, and h2 is just equal to r cos theta 2. Right, let's replace numbers in there. So we'll have minus 40 by 9.81, okay, by 2 cos 60 degrees. Then this is just equal to half times 40 times v2, okay, minus again 40 by 9.81 2 cos 0, okay, 0 degrees. Okay, so sorry, I want to just move this. I've choose a lot of space. I'll write that negative that I just deleted. I just want to move it this side like so. I'll write that negative. So let's find what this v2 is. v2, you can calculate it directly. I'll not write all the steps here. So we have minus 40 times 9.81 times 2 cos 60 plus 40 times 9.81 times 2 cos 0 and divided by 0.5 times 40, okay, and square root of that. So we have our v2 as 4.43 meters per second. So minus 40 by 9.81 by 2 cos 60 plus 40 by 9.81 by 2 cos 0 divided by 0.5 by 40 and square root of that, 4.43. So we have our v2. So we can now apply the equation of motion. So we'll say, so that we find the tension. So if we are to section this, let's section it so that we include this information. Let's section it somewhere there. We're going to have some tension force like so. Alright, so let's call that as T. We call that as T. We need that for us to find the forces in this particular post. So for the equation of motion, we'll say summation, and motion, of course, in this particular case is in this direction. Motion is in this direction. This is our AN. Okay, so summation of forces along the N axis is just equal to M AN. Okay, and what do we have? We do have T minus W cos theta. Okay, and this theta here, it is theta 2. Okay, theta 2, right? Then this is equal to M AN, and our AN is just V2 divided by rho, okay, where rho is equal to R and it is equal to 2, and our theta 2 is equal to 0 degrees. Right, let's write this. So we have T is just equal to M V2 squared divided by R plus W cos theta 2, and this is equal to 40 by 4.43 squared. Okay, let's find the tension. 43 squared divided by 2. I think there is less space there. Let's write it down here. So say T is just equal to 40 by 40.43 squared divided by 2 plus 40 times 9.81 cos 0. Therefore, our T is just equal to 40 times 4.43 squared divided by 2 plus 40 by 9.81 cos 0. Right. So our tension just becomes 784. Okay, this is 784.898 newtons. So this is our tension in our pore. Mind you, the pores, they are 4, but they are symmetrical. 2 of them are symmetrical, and these are 2 force members, right? Let me calculate this again. 40 times 4.43 squared divided by 2, which is our radius of curvature, plus 40 times 9.81 cos 0. Alright, 784.898. Alright, so we need to divide this later on. So using joint method, okay, let's say using joint method, to calculate the member forces at A. So this is joint A, this is A. So at A, we do have this particular tension force, which we just calculated. We have this tension force that we just calculated. And then we have these 2 forces we have, and they are just both in compression. This one and this one, right? These are both in compression like so. Alright, so we'll have components. We're going to have component in this direction like so, and then we'll have 2 components in this direction like so. Alright. Like so. So this one here is point A. Let me make it red. This is point A. This is A. Alright. So I want to make mention that force AB is equal to, let's call this one here C. Okay, is equal to AC, which we are just going to say is equal to F. Okay. But there are 2 of them, so we'll say 2AB is equal to 2AC, which is just equal to 2F. Okay, there are 2 sets there, right? So this force here, these ones are equal, so this we can just say this is 2F, this is 2F, and this is 2F. And the angle there is, this is 30 degrees, and also this is 30 degrees. So with this in mind, you can say this one is just going to be equal to 2F sine 30, and so is this one 2F sine 30. And then this one down here is just going to be equal to 4 F, okay, cos 30, right? Because there are two poles of this, right? 2AB just equal to 2 that, okay? So once we find one set there, we'll have found the other set that side. Okay, and here we have 2 of them, but there are 4 in total. Alright, so let's sum up the equations here. So we'll say summation of forces in the y, this is just equal to, so we just want to distribute these forces along those directions. This is equal to 0, going up being our reference. And what do we have here? We said this one here, it is t, this one here is t, right? So this we have 4F cos 30 minus t, this is equal to 0, and therefore our F is just going to be equal to t divided by 4 cos 30, and this is equal to 784.898 divided by 4 cos 30. So the member forces here are just going to be equal to, so divided by 4 cos 30 degrees, like so. So this is just 226.58 newtons. Alright, and it is compressive. Alright, so I can even just say in brackets there, I say C for compressive. Alright, so 784.898 divided by 4 cos 30, 226.58. Alright, I guess this is about it. We have found the force developed in member in all the 4 posts, right? In AB and AC, and also the other pair, the other side, right? So I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.